Hello everyone, I am Dr. V.S. Shinde, Assistant Professor, Department of Chemistry, KTHM College, Nasik. Student, today we are going to see a topic from CHI 230, that is Coordination and Bioinorganic Chemistry, and the topic is term symbol and microstates. Means we are going to study how to calculate term symbols, that is RS term and GS term, and how to calculate different types of microstates. So student, in today's lecture we are going to see term symbol. It means we are going to see RS term or RS coupling. RS is nothing but Russell Sounder coupling or Russell Sounder term. We can say LS coupling, and also we can say GS term, that is ground state term, or for this ground state term we can say full spectroscopic symbol term. So under the term symbol we have to see how to calculate RS term or GS term, that is full spectroscopic symbol, which is totally based on interaction of L and S values. And the next one, we have to see how to calculate number of microstates. Actually, there are 4 different types from which we can calculate different types of microstates. Exactly what is microstates? There are different number of possibilities to arrange electrons in a given configuration or in given Mulligan symbol, or maybe for given terms. Okay, so in today's lecture, we are also going to see how to calculate number of microstates and term symbol. Term symbol. So basically term symbols are nothing but RS terms or GS terms. So what is RS term? RS terms are Russell Sounder terms. Russell Saunders term. Or we can say LS terms or LS coupling. RS terms or RS coupling or LS coupling. This LS coupling or RS coupling is nothing but the interaction of L and S terms. L and S terms. So let's see the representation for RS term. So representation for RS term. So 2s plus 1 L, this is nothing but the RS term, and if you want to calculate a GS term, that is ground state term, so the formula to calculate ground state term is 2s plus 1 L and J. To calculate RS term, the formula is 2s plus 1 L, while to calculate the GS term, the formula is 2s plus 1 Lj. GS term is also called as full spectroscopic symbol. It is also called as full spectroscopic symbols. Okay, so let's see what is this 2s plus 1, what is this L, and what is this J. Suppose we have to calculate RS term. So what is this A? What is this S? This S is nothing but spin quantum number. Spin quantum number. Okay, this S is nothing but spin quantum number, while this whole term, that is 2s plus 1 is spin multiplicity. Spin multiplicity. While this L is orbital angular momentum. L is orbital angular momentum. while this J is total angular momentum. J is total angular momentum. So this is the representation or formula to calculate RS term or GS term. I again repeat, this RS term is nothing but Russell sounder term which is based on LS coupling or RS coupling. While this is your GS term which is also called as full spectroscopic symbol. This is the formula, that is 2s plus 1 Lj to calculate the full spectroscopic symbol, and this is the formula to calculate RS term, that is 2s plus 1 L. Okay, so let's see what is exactly L. See, suppose L means orbital quantum numbers, that is suppose that number starts from 0, after that 1, 2, 3, 4, 5, 6 and so on. So for this number there are some spectroscopic notations, or we can say spectroscopic symbols, that is spectroscopic notation or spectroscopic symbol. Suppose L value is 0, then spectroscopic notation is S, then P, then D, F, G, H, I and so on. Okay, this is nothing but the values for L, and these are the spectroscopic notations for that specific values. Okay, now the question is that how to calculate J, that is how to calculate total angular momentum. Okay, so there are two formulas to calculate this J, either L plus S or L minus S. Okay, when there is L plus S, so for example, suppose we have P2 configuration. Suppose we have P2 configuration, we know very well the orbital, P orbital. So as we have two P electrons, so one electron is here, one electron is here. Means this orbital or this configuration is less than half filled. Then if we have configuration which is less than half filled or exactly half filled, that time we have to use L minus S. When the configuration is half filled or less than half filled, that time we have to use L minus S, and when the configuration is more than half filled, that time we have to use L plus S. Okay, this is nothing but the calculation for J, means L plus S or L minus S. If the configuration is less than half filled or perfectly half filled, then we have to use L minus S, while if the configuration is more than half filled, that time we have to use L plus S formula. Okay, so let's see the examples. Okay, before starting example, let's see the steps, that is how to calculate RS terms. Let's see the steps for calculating of RS term or GS term. So the first step is calculation for ML value, that is summation of MLI. The next step is calculation for MS values, that is summation of MSI. The third step is we have to calculate 2s plus 1, that is spin multiplicity. That is 2s plus 1. And the last step is calculation for J value, that is either L plus S or L minus S. Okay, these are the 4 steps to calculate RS value or RS term or GS term. First of all, we have to calculate ML value, then we have to calculate ms value, then we have to do calculations for 2s plus 1, that is spin multiplicity, and the last one is calculation for j, that is l plus s or l minus s. So let's see the examples. Let's see first example, that is P2 configuration. Suppose we have P2 configuration and we have to calculate its RS term or GS term. So let's see how to calculate. As we know that the first step is calculation for ml value. So we have p orbital, this is p orbital, 0 plus 1 minus 1. I will not explain you that how to fill electrons because this is the basic one and I think all are know these concepts. So let's see 2 electrons, 1 and 2. Now the L value, so calculation for L value. See, suppose I will tell you a simple trick. Suppose we have 1 electron in this orbital, so 1 into 1 is 1 and 1 into 0 is nothing but 0. So 1 plus 0 is equal to 1. So L value is 1. We have L value is 1 and I just told you that as the L value is 1, the spectroscopic term or spectroscopic notation for one value is P. Okay, hence we can say X is equal to P. This is our term. Now the second step is calculation for MS value. Calculation for MS value. Okay, S means spin quantum number. So see, here there are 2 electrons which are in upward direction. So obviously plus half for each one. Plus half, then plus half is equal to 1. Okay, so the S, that is spin quantum number, is 1. Hence, to calculate 2s plus 1, we require this S. So 2 into 1 plus 1 is equal to 3. Okay, so the spin multiplicity for P2 configuration is 3 and we have the term 1. Sorry, the term P. That's why I write here P3. Okay, so now the calculation for J value, that is last one. Calculation for J value. See student, as we know, the configuration is less than half filled. So we can directly write here L plus S to L minus S. To L minus S. Now we have L value and S value. What is the L value? L value is 1 and S value is 1. So 1 plus 1, 2, 1 minus 1. 2 to 0, but we know that the configuration is less than half filled. That's why we have to consider this term, that is L minus term. Hence, the final GS term for P2 configuration is 3P0. Okay, this is nothing but our full spectroscopic symbol or GS term, or if we hide this, that is J value, then 3P is nothing but RS term, and if we show both all these 3 values, all these 2 values along with the spectroscopic notation, so this is the GS term or FSS term, that is full spectroscopic symbol. Okay, let's see the next example. Now I am taking here cation. And from that cation, we have to calculate its GS term. Now see, suppose we have Fe2+. We know the atomic number of Fe, that is atomic number of Fe is 26. The valence electronic configuration for Fe is 3d6 4s2. But as Fe carries +2 oxidation state, Fe carries plus 2 oxidation states. So obviously there is loss of 2 electron from outer orbital, that is from this orbital. Hence the electronic configuration is 3d6, means we have d6 configuration. Okay, now we have d6 configuration and we have to calculate a GS term for this d6 configuration. So let's see, d6, in D there are 5 orbitals, 1, 2, 3, 4 and 5. Okay, so 0 plus 1 plus 2 minus 1 minus 2. We have 6 electrons, so 1, 2, 3, 4, 5 and 6. Okay, means we can say now the configuration is more than half filled or greater than half filled. So the first calculation for ml value. Let's see the simple one. This is plus 1. So plus 1 minus 1 get cancelled. 0, that is 1 into 0 is equal to 0. So no use of that electron. Again, this 1 and this one get cancelled. Now we have only 1 electron in plus 2. That's why ml value is 1 into 2 is equal to 2. Okay, as we have L is equal to 2, hence X means spectroscopic notation is D. Spectroscopic notation or spectroscopic symbol is D. Now next calculation for MS value. This is paired electron, that is plus half minus half get cancelled. We have only 4 electron which having upward spin, means plus half and plus half, that is 4 by 2. Hence S, that is spin quantum number is 2. Okay, so the calculation for 2s plus 1, that is spin multiplicity, 2 into 2 plus 1 is equal to 5. What is spin multiplicity? 2 into 2 plus 1 is 5. So we can write like this, D5. This is our RS term, but still the calculation of for J is remaining. So let's see the calculations for J value. Okay, as usual, L plus S, 2 L minus S. What is L? L is 2 and what is S? S is also 2. So 2 plus 2, 2, 2 minus 2, 4 to 0. But we have configuration which is greater than half filled. That's why we have to consider this value, that is L plus S. So the final GS term is 5D4. This is nothing but your GS term or full spectroscopic symbol. Okay, in previous example, we are taking P configuration, that is P2. Now, we consider here D. Now, let's see the F configuration. Suppose I have example, that is terbium 3+. The atomic number for terbium is 65 and the valence electronic configuration is 4f8, 5d1 and 6s2. But we know that as Tb carries plus 3 oxidation state, so there is loss of this 3 electrons because these electrons occupies the outermost shell. So the final electronic configuration for Tb3 plus is 4f8, means we have F8 system. Okay, we have F8 system. We know the F orbital 1, 2, 3, 4, 5, 6 and 7. So 0 is here, plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. Okay, as we have 8 electrons, 1, 2, 3, 4, 5, 6, 7 and 8. So let's see the first calculation for L value, that is summation of MLI but I explain here a very simplest trick how to calculate ml. So -2 plus 2 get cancelled, +1 -1 get cancelled, 0, there is no use of this electron because 1 into 0 is equal to 0, and 1 from 3 and -3 get cancelled. Now we have only one electron in this orbital, that is 1 into 3 is equal to 3. That's why L is equal to 3. As L is equal to 3, the spectroscopic notation is F. So X is equal to F. Okay. Now next, calculation for MS value, that is spin quantum number. See, as this one is paired, so +1 -1 get cancelled. 1, 2, 3, 4, 5, 6. That is, and everyone having upward orientation or upward spin. So +½ +½ +½ +½ +½ and +½ Okay, so equal to 6 by 2, that means 3, that is S is equal to 3. As S is equal to 3, now the next step is calculation for spin multiplicity, that is 2s plus 1. As we have S is equal to 3, 2 into 3 plus 1 is equal to 7. Okay, that's why the spin multiplicity for TB3 is 7. So finally we can write RS term, that is F7. But still we have to calculate J value to show the full spectroscopic symbol. Now the last step is calculation for J value. J is equal to L plus S to L minus S. What is L? L is 3 and S is 3. Okay, so 3 plus 3, 2, 3 minus 3. So 6 to 0. But we are interested in L plus S because the configuration is more than half filled. That's why the final GS term is 7F6. Okay, this is our final GS term, that is ground state term or full spectroscopic symbol. Okay student, I think these all three examples are more than sufficient to how to calculate RS term or GS term or full spectroscopic symbols. This is totally based on interaction between L and S. Okay, L means angular orbital momentum and S means spin quantum number. Okay, so let's see, we have to calculate microstates. How to calculate microstates. Okay, let's see how to calculate microstates, that is number of microstates. See, if any term is given or any configuration is given or any Mulligan symbol is there, we can calculate its number of microstates. What is meant by exactly number of microstates? Means total number of possible arrangement to arrange the electron of a given electron. Means if P2 configuration is there, suppose P2 configuration is there, means we have 2 p electrons, so its total number of arrangement, possible arrangement. For example, we have 2 electrons, so I may arrange like this, these 2 electrons. Again, I may arrange like this. I can arrange like this one, pairing. Okay, and so on. Actually, for P2, there are 15 number of microstates. Means there are 15 possible arrangement by which I can arrange these 2 p electrons. Okay, so let's see. There are basically 4 types of microstates. So let's see one by one. Suppose any configuration is there, that is, I take same example, P2. So, to calculate number of microstates for any configuration, the formula is n factorial and n minus n factorial. Okay, what is this capital N? So, n is total number of electron capacity of that given orbital. Okay, suppose this is p orbital. We know that there are 3 orbitals in that p. So total number of electron capacity for that p orbital. So total number of electrons is 6. Are 6. So what is this n? The given electron or present electron. Given electrons. So let's see how to calculate microstates. So n factorial, that is 6 factorial upon this small n means given electron. We have 2 electrons, that's why 2 factorial and 6 minus 2 factorial. Let's see the calculations. 6 factorial, 6 into 5 into 4, 3, 2 and 1 factorial upon 2 into 1 factorial and 6 minus 2 are 4 factorial. So 4 into 3 into 2 into 1 factorial. Okay, so this 2 get cancelled, this 4 get cancelled, 3 get cancelled, again this 1 get cancelled and 2 into that is 3. So obviously 3 into 5 is equal to 15. So total number of microstates for P2 configurations are 15. So there are 15 arrangement for this 2 electrons, 2 p electrons which can be arranged by different possibilities. Okay, so this is the first type. Let's see the second type. Second type means configuration is in combination. Suppose this is the type 2. Type 2, suppose we have P1, D1 configuration and we have to calculate its microstates. So let's see the calculation for P1. So as usual n factorial upon n factorial n minus n factorial. Same for D, n factorial n factorial n minus n factorial. So n means total number of electron capacity by p orbital. So 6 factorial upon this is we have only 1 electron, that is 1 factorial, and n minus n, that is 5 factorial, into total number of electrons in d orbital are 10. So 10 factorial upon we have only 1 electron, that's why 1 factorial, and 10 minus 1 9 factorial. But see, we have to calculate, so 6 into 5 factorial, 1 factorial no use actually, and 5 factorial. So into 10 into 9 factorial, I want to cancel up to 9 factorial, that's why I written here, and 9 factorial. 9 factorial, 9 factorial gets cancelled, 5 factorial gets cancelled, we have only 6 and into 10. So the total number of microstates for P1 D1 is 60. So we can arrange by 16 way to this P1 and a D1 configuration. Okay, this is the type second. Now let's see the type third. Suppose any term is given, for example D2, F3, then G1, S1, okay, like this. Suppose we are going to say this D2 term. Okay, suppose D2 term is given and we have to calculate is microstates. So the formula to calculate microstates for any given term is 2s plus 1, that is spin multiplicity, which we have already seen in RS term, and 2l plus 1. Okay, the formula to calculate number of microstates for this term, that is D2 term, formula is 2s plus 1 and 2l plus 1. We know the 2s plus 1 because in D2 system or in D2 term, spin multiplicity is already given. That is 2 into 2l plus 1. Now we have to calculate L value for D spectroscopic notation or D spectroscopic term, and we know that as L is equal to 0, 1, 2, 3, the spectroscopic notations are S, P, D, F. Okay, now For the D, L value is 2. Hence, 2 into 2 plus 1. 2 into 2 plus 1 is equal to 5. So, 2 into 5 is equal to 10. So, the total number of microstates for D2 term is 10. Okay, this is the type 3rd. Now, let's see the type number 4 or last type. We know Mulligan symbols and its degeneracy for all Mulligan symbols. Suppose Mulligan symbol is given and we have to calculate its microstates. So, how to calculate? Suppose twice T2G is Mulligan symbol. 1 A1G is also Mulligan symbol, or thrice EG. Twice EG. This is also Mulligan symbol. So, simply what is the degeneracy for A Mulligan symbol? The degeneracy for A is 1, for E degeneracy is 2, and for T Mulligan symbol degeneracy is 3. So, simply the formula to calculate, this is type 4. Formula to calculate the number of microstates in case of Mulligan symbol is 2s plus 1, that is spin multiplicity, into degeneracy. Degeneracy of that particular term of that particular Mulligan symbol. So, what is, suppose the example is T2G twice. So, what is 2s plus 1? The spin multiplicity is already given, that is 2 into degeneracy. So, what is degeneracy for T? Degeneracy is 3. So, the total number of microstates are 6. Okay. So, this is the calculation for number of microstates in case of Mulligan symbol. So, student, we have seen here how to calculate number of microstates in 4 cases. If configuration is given, the formula is different. If any term is given, the formula is different. And if Mulligan symbol is given, the formula is different. Okay. So, thank you.